we understand even with best sorting algorithms, we need at least n log n. Okay, so something like a selection sort is not a solution. Okay, so it needs n square, but the quick sort needs n log n, right? But for the worst case, it needs n square, but on average, it needs n log n, so which is good. So we have other kind of sorting algorithms with n log n time complexity. Okay, so we have many good sorting algorithms. As long as the time complexity is n log n, then they are kind of the best. Okay, but we don't have one best sorting algorithm in general. It depends on the data samples. It depends on your computer situations. Like some algorithms need lots of memory space. Okay, then it depends on your computer system. Okay, so if your computer system doesn't have that many memory space, then that's not a good solution. Or as we've seen with the quicksort algorithms, sometimes when we have some prior knowledge about the data, okay, so maybe the data is pretty much sorted, then the quicksort is not the best solution. Probably we have to think about some other sorting algorithms like merge or heap or radix or whatever. Okay, so it depends on your computer system and it depends on your data. Okay, so you have to understand how these sorting algorithms are working. Okay, you have to understand the principles and the fundamental limit, pros and cons, and then depending on your situation, you have to pick your own sorting algorithms. Okay, so now we'll talk about some other options too. First one is a merge sort. So merge sort has some simple idea. So we start from quite a simple idea. Okay, first let's talk about the merging. So when we have a two sorted list, then we can merge these two lists, and in the merged list they are sorted. Okay, so something like this. We have a good example here. So we have one list basically, but this list is composed of two sublists, and one is sorted and the other one is sorted. But when we look at this one as a one list, then they are not sorted. But when we look at this sublist separately, they are sorted. Okay, then what should we do? We want to merge these two sublists into a sorted list. Okay, then the idea is quite simple. We have three variables indicating the boundaries of these two sublists. So I is the first element and m is the last element of the first list, and m plus 1 is the first of the second list, and n is the last element of the second list. Okay, so I goes from here and j goes from m plus 1. And how can you combine? How can we merge these two lists? So basically we compare two elements here and here. Oh, 1 is smaller than 11, so we copy this one, and then I goes to the next one, and we compare 5 and 11. 5 is smaller. Okay, then I goes to the next one, and 26, 11. Yes, 11 is smaller than 26. Then J goes to the next one, and we compare 26 to 15, and the 15 is smaller. And then J goes to the next one, and 26 is smaller. Okay, then I goes to the next one. 59 is smaller, and then next one 61 is smaller, and then finally 77 is the last. Okay, so by this simple algorithm, then we can merge two sorted sublists. Okay, so as long as we have two sorted lists, then we can merge. Okay, then we can take one step further. Okay, so when we have a two, so look at this one. When we have a two sorted list, then we can merge these two lists to make a longer sorted list. But in the previous step, so we have a sorted list here and here, then we can merge these two sorted sublists to make a one longer sorted list. And also this one sublist can be a result of this merging. Okay, and then this one is also a result of merging of these two. Okay, so then we can start from this. Okay, so we can start from individual elements. And when we focus on one element, this one is sorted. Yes, obviously. Okay, so you have one list, well, you have one element in your list. Is it sorted? Yes, definitely. And then we combine and we merge and we merge, okay? And then we have a little longer sorted list and then we merge and merge. So from individual elements we can merge and merge. Finally, eventually we can get a sorted list. This is a merge sort. Okay, so let's talk about merge function first. Okay, we have a two list. Actually, this one is an input list and this one is output sorted list. Okay, so list is a long list with lots of elements, and we have three indexes. So I is here, and M is here, and N is here. It means we are focusing on this sublist. Okay, this is list, but we are focusing on this, and then in this sublist, from I to M, these are sorted, and from M plus 1 to N, these are sorted. Okay, so let's assume that we have two sorted sublists as a part of this list. Okay, then initially J is M plus 1. Okay, so J is here. And we have one major while loop. So I should be less than or equal to M, and J should be less than or equal to N. So when we compare I's key and J's key, if I's key is smaller than J's key, then okay, we have sorted. So we copy I's element to sorted list, and then we increase K and I. So I goes to the next one and K goes to the next one. Otherwise, it means J's key is smaller than I's key. Then we copy this one, J's element, to a sorted list, and then we increase K and J. Okay, so in this case, what if I's key and J's key are the same? Then we copy J. Or if you want, you can have this here. Okay, so that in this case, it would be stable. But without this equality, then this algorithm is not stable. Okay, so after this while loop, when we merge, we finish one side earlier than the other side. Okay, let's say the last element is smaller than the middle element. Okay, let me draw one more time here. So we are merging these two, and this element, this is the largest one from this one, but this one is smaller than this one. Okay, then we copy this one into we copied this one and these ones to our sorted list. Okay, but then what about this part? So we have some left over there. Then we have to copy all of them to sorted list. So after this while loop, we check if I is larger than M. If I is larger than M, it means I passed. It means we copied the left side, okay, and we finished left side earlier. So it means we have some left over on the right side. So we just copy the right side to sorted list while increasing K and J. Otherwise, until I is smaller than or equal to M, we just copy all of them from the left side. Okay, this is it. This is an implementation of a merge function. Okay, so you can try this one more time. Okay, so we can compare I and J, and I is smaller than J, so we copy this one, and I increases by 1, so now we compare this one, and the 5 is smaller, and then the I increases, and the 11 is smaller, and J increases, and 15 is smaller, and then increases, and 26 is smaller, and 59, 61. That's it. And then we finish the while loop, and then we have leftover on the left side. Then we have to copy 77. Okay, that's it. Okay, so in the previous slide we talked about merge sort. Okay, but that doesn't include all of them. Just the merge function is not enough to sort the whole list. Okay, basically, given a non-sorted list, then what should we do? Basically, we divide this list into two sublists, and at this point, these two sublists are not sorted yet. And then let's assume that we can apply some sorting algorithms. Okay. And now we have a two sorted list. Then we can merge to get a sorted list. Okay. So at this point, if you want, you can use some other sorting algorithm too, but that's not what we want basically. Okay, if you apply quick sort algorithm to sort here, then it works, but that's not that beautiful. Okay, so in the merge sort, without any other sorting algorithms, merge sort will actually take care of this sorting too. Okay, so we will talk about that in the following slides. Okay, so this is a full implementation of merge sort. So given this list and the output list, and we have two integer variables, low and high. So given a two list, okay, so this is our list and this one is the sorted list. And originally when we call this merge sort from a main functions, okay, then low will be 0 and high will be n-1. So let's say we have 5 elements here. Okay, then low is a 0 and high is 4. Okay, then from main function when we call, then we check if low is smaller than high. Yes, 0 is smaller than 4. But we have 5 elements here. That's too complicated. So we will divide this list into two sublists, and mid will be 2, right? And then recursively we call merge sort again. So at this point, low is a 0 and mid is 2, and mid plus 1 is 3, and high is 4. So we call this merge sort twice. And first one is focusing on the left side, and the second one is focusing on the right side. And by merge sort, we assume that left side is sorted and the right side is sorted, and then we can call this merge function. Okay, this is it. This is enough to sort. Okay, if you're familiar with the recursive solution in general, then this function is really simple. You can get it really quickly. But if you're not familiar with the recursive approach, then you might have some hard time to understand this function. But I strongly recommend you to go back to the recursive algorithm chapter, okay, and study the Hanoi Tower algorithms and Fibonacci and factorials, and then come back to this one. Okay, now let's talk about time complexity. Okay, so for this merge function, we need the linear time complexity to finish this function. And the question is, how many times do we have to call this merge sort? Okay, when we call, every time we call twice, but in the big O notations, the constant means nothing. Okay, so how many times do we have to call this? Basically, we are calling this one this many times, log n. Why is that? Whenever we call, the length of this sublist will be the half of before. Okay, so it's like a binary search. Whenever we go down, then we can have twice as many nodes as before. Okay, likewise, it's a little opposite, but you know what I mean. Every time it becomes the half. Okay, so We talked about this one with a quick sort, right? So in the quick sort, we call the quick sort log n times. Likewise, we call this merge sort log n times. So we have n time complexity, and we call that log n times. So in total, we need n log n time complexity. Now, this example explains how merge sort works. Okay, so we have unsorted list here. Okay, now this list is too long, so we split, we divide. So now we have a left side and right side. So basically we will do the same thing on both sides. So let's focus on the left side. And left side still is too long, so we split, we divide, and then we have 2, and then still this is too long, and then we divide, and still this is too long. So 2 elements in a list, so it's too long because we are not sure if this list is sorted. So we split one more time. So now we are sure that this one is sorted and this one is sorted. So now we can merge these 2 to get a sorted list. Likewise, we can keep doing this until we get one merged list. This is how merge sort works.